So it's so first of all, thank you for inviting me here, Muriel, and thank you very much. And thank everybody for sticking around until 4 o'clock. So to reward you, I'm going to play a little movie. Now I have to apologize ahead of time. The movie's a little herky-jerky because I took it with my cell phone, but maybe it's maybe that makes it a little more realistic. So what we're going to see here is actually a presentation in Espoo, Finland, which is at our headquarters, of centralized RAN, a feature we call centralized RAN, which is what we believe is really the first feature to do joint reception in a sort of an ultra-dense setting. So in here, let me just stop for a second. So this is a conference room. Maybe it's about this size. It has 10 remote antennas. So you'll see in the corner, I'll point it out, but the radios are sort of on a mount in the corner, and they're fiber connected to the antennas. There's 10 antenna sites, which represent 10 LTE cells, so 10 physical cell IDs, 2 antennas each, and then there's 30 UEs or 30 devices in the room. And what will happen is you'll see people going around and starting those devices up, and the devices take pictures periodically and they upload them to the network. And when the upload is complete, they take another picture and they upload it. And there's 30 devices, okay? So that's what you'll see here. I don't know if I can mic the sound. Oops. Where's my speaker? Can you hear this? So he's not saying this, but the curve you see there is the sum across all 10 cells. It's the throughput. And then the dial, the speedometer dial is again, summing the throughput across all 10 cells. And as they add more devices clicking, the clicking sound is the pictures, you'll see the throughput increase to a point here, and then it levels off. All right, be patient. The cool thing happens pretty soon. It's coming. So this is 10 LTE cells producing 30 megabits per second. So it's kind of bad, right? It's like 3 megabits per cell. Now you turn on the feature. This is like what you want to see, right? For stuff that you build. Yeah. So you know what's happening here is this is the promise of joint reception that we all sort of heard about 10 years ago or something. So we were able to actually build this at Nokia. Now the use case is somewhat narrow, and that again I think fits the theme of 5G. There's a lot of little narrow use cases, but this particular use case was inspired by a stadium. So in stadiums during mass events, you might not know this, but the uplink data throughput is equal to the downlink. Okay, this is maybe well known now. It wasn't so well known a couple of years ago, and so but LTE is not designed that way. It's not designed, so the uplink is actually much less spectrally efficient than the downlink. So we came up with this feature to sort of equalize it in stadiums. And it worked out. And I was telling Andrea, one of the reasons we were able to do this is that we use DSPs in our baseband unit. So we're able to change the software and basically use the baseband unit for something that it was really never designed for, which is to pull in this case, each cell is able to access the antennas of 5 other cells. So it's basically antenna sharing, antennas from 5 other cells, and then down selecting and then running basically an 8 antenna receiver, on the down selected thing. So the reason I wanted to show you this is that this kind of technology on the uplink will be very prevalent, I think, in 5G. And we really want to design systems that, again, you've heard several speakers talk about, getting rid of the concept of a cell or various flavors of that, right? So why is a user attached to a cell, and that's the only place it can get its data, and so on. So here's the beginning of that. It's also the beginning of what Paul talked about with Cloud RAN. So here, it's actually this first step towards disconnecting the physical cell from the hardware that it runs on. Because here, in order to actually build this 12RX receiver, we had to share DSPs among cells. And so we made that first step towards disconnecting the cell from the hardware that it runs on. That's going to be a very important concept, I think, going forward in 5G as well. So that is that. And now to my fancy slides.
Into the movies?
Excuse me?
No more movies?
There is another movie. There's another movie. You have to wait. Wait till the end. Just a couple words about Nokia Networks, because I'm not sure everybody knows about Nokia Networks. So we have a services branch, which is number 2 in telecommunication services. We have 100 years in telecom. We operate in 120 countries. We have 145 LTE contracts throughout the world. We are the number 1 macro base station vendor from competitive assessments. In global market share, we're number 3. And hopefully with the unification of Alcatel-Lucent and Nokia next year, we will become possibly number 1. We have 50,000 employees, and net sales in 2014 was 11.2 billion. So that just tells you a little bit about Nokia Networks. So I think this this material has been covered, but the idea here is that you have these Gs every 10 years, and here what's happening though in this particular G is that the world has recognized that there isn't the wireline internet and the mobile internet. There's going to be the internet, and it's going to be used for real-time control. It's going to be used for next generation media, whatever that might be. For example, something that didn't come up yet was, I don't know if you guys have experienced this yet, but these virtual reality headsets, right? You can put them on, you're in downtown Chicago or you're whatever, but wouldn't it be great to, you know, use one of those to play tennis outdoors? So what's the data rate that you would need and the latency requirements you would need to play tennis with somebody who's, you know, 1,000 miles away? You know, I mean, just sort of think about it. It's, I think you're talking now in the gigabit probably per second, you know, range. So, and the latency again has to be near zero. So this is our chart for looking at that. So we go from audio to visual to tactile. And when you go to tactile, now you need 1 millisecond latencies. So again, I'm not going to spend a lot of time because you know, my colleagues have already spent a great deal of time on this kind of stuff. But this is our view of the requirements. So, you know, 10 years battery life, ultra low cost machine to machine. There's 100 times more devices, 10 gigabit peak rates, which, by the way, Nokia's already achieved at 75 gigahertz. We have a working demonstration that we showed at Mobile World Congress, 10 gigabits per second over the air, working with National Instrument. 100 megabits per second on the cell edge. So this is the sort of homogeneous experience that other speakers have talked about. So we're talking about sort of a floor of 100 megabits per second wherever you go. 10,000 times more traffic based on, again, probably Cisco's analysis. This ultra reliability. So, you know, when you're using this to monitor health, for example, I mean, it can't be going down on you, so it has to be ultra reliable, and then the 1 millisecond latency. So very, very tough requirements, but you know, we think those are the right goals for 5G. So what kind of technologies? We'll use massive MIMO, we'll use massive beamforming, which is not the same thing. We will use centimeter wave and millimeter wave technology. We'll try to use new waveforms and new modulation techniques. I think Yuri's talk was very interesting because you know, maybe when the channel is a gigahertz, you have a gigahertz channel, maybe the blocks are big enough to start looking at different modulation schemes besides QAM and so on, and maybe those start making sense. So multi-radio access technologies, so integrating multiple, we talked about this ability to, so Google is kind of integrating LTE and Wi-Fi, but you know, I think as these new access technologies come in, it will not be like LTE, it'll be like 3 versions of LTE or something like that, right? And they all need to be integrated. Radio virtualization, so Paul talked a little bit about that, and flexible networking. And here, again, I think there's probably a role for artificial intelligence in communication networks that we maybe haven't really investigated yet. I think it's an opportunity, and I do think that we should make the assumption that Moore's law will continue, and then play that out and see, you know, what is it that would happen. I think that's, you know, a better path right now than saying, well, you know, I think Moore's law is going to stop in 6 years or whatever. You know, it's just a matter of, it's just an attitude that you take, I think, more or less. I don't know whether Moore's law will continue. And like you said, you know, there's people on both sides, and all I know is that the hardware people are very creative, and they're always coming up with new ways to do stuff. So, so let me skip this. Here's what we feel is that it's not necessarily true, but there's a very strong chance that a new radio access technology would be motivated by either the new spectrum or lower latency latencycy latencycy requirements or specific use cases. Something will motivate this, and so as an industry, we need to investigate those things, and we need to start looking at them. And that's, to me, what 5G is. It's a research program that gives the industry options, gives the operators and the vendors options. So, so again, this is kind of a requirements slide with a fancy build. But so, ultra dense, ultra reliable, low latency, ultra deep, meaning massive machine type communications, all very important. So LTE satisfies each one of these things to a certain degree, and as you go around this circle, you see the key metrics, right? Peak data rate, user experience, mobility, latency, connectivity, energy efficiency, traffic volume density, so that's sort of bits per second per square mile type of thing. But we do believe that 5G will be important to actually get to those requirements. So I think people have talked about this. There's we divided into three technologies really: millimeter wave, centimeter wave, and then below 6 gigahertz. And they all have their unique use cases. And the thing that divides them up is that column on the on your right-hand side. So in millimeter wave, it will be more noise limited. In centimeter wave, you'll have some strong interference handling that'll be required. And then in below 6 gigahertz is used for the full coverage. So that's the role that each one of those will play. And so, when you do research into them, you kind of want to keep that in mind. We also believe that for millimeter wave, you'll probably do low rank MIMO. I think this was mentioned before, this business about being able to fit, say, 64, 128 antenna elements on maybe a 1-inch chip, right, and then be able to focus pencil beams at 2-3 degrees and use the gain rather than the spatial dimensions of the channel, right? So you're basically going to make a simple radio that has a high gain antenna, so you point it at a user within 10 milliseconds. You've given them, if they're getting a gigabit per second, within 10 milliseconds you can transfer 100 megabits to them, and so you're basically going zap, 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 zap. So that's the vision, and I'll show you. I'll show you another movie towards the end because I promised to, and I'm almost there. So I have lots of slides here. Let me just go ahead and show you that movie, and then we will take some questions. And let me just flip through these. By the way, I did want to mention this work that we did in conjunction with NYU Poly on propagation of millimeter wave. I think it had some counterintuitive results, right? And showing the feasibility of doing things at millimeter wave. So there's a very good paper out on that you can take a look at. And in the massive MIMO area, I'll just point out, again, we are working with universities and vendors on these chip-scale antennas, if you will, for massive MIMO. So here's the proof of concept. So right now we're using a lens antenna for this, I think it's at 73 gigahertz if I'm not mistaken. And so first of all, you kind of get it working and you get data to transfer. So we did that last year. This year, what we're doing is we're able to move the device around in the room and get the beam to track it. So it's a 3-degree beam, and it essentially tracks the UE, and I will show you that video now if YouTube will cooperate.
research specialist at Nokia, focusing on 5G research projects. Today at the Arlington Heights campus, we're going to demonstrate Nokia's 5G millimeter wave proof of concept system. Our demonstration will show the feasibility of using directional antennas for pedestrian mobility at the 70 gigahertz band. In our experimental system, the access point is located about 8 meters away from the user device.
Oh, okay.
Our access point is using a dielectric lens antenna.
We're going to fix the sound. Good. Good, good. Just give me 1 second. Where's your volume? Right here. There it is. Might be too loud.
That beam is steerable and can track our user device. We will now move the user device through the steering range of the access point. When the user device moves side to side, we expect that the access point's lens antenna will be able to track the user device. Remember that the access point's antenna has a narrow 3-degree beam width, so it needs to follow the device to maximize signal quality and data throughput. The user device display shows a virtual representation of the access point's front panel, showing the lens antenna and also the LED display matrix. The LED matrix indicates the selected beam. Right now, the system is transferring data in the downlink at 2 gigabits per second. This is just one of the many research areas which Nokia and leading operators like Docomo currently explore in their research.
Nokia and NTT Docomo have a successful history of cooperative research.
There you go. That's the marketing stuff. Right. So I just wanted to show you those 2 videos to show you that, well, you know, things are happening. People are building stuff and testing it. And, you know, the next step for this demonstration is to do a handoff to show, for example, a handoff from one access point to another when you go behind some obstruction, or to show that you can actually bounce the signal off of a wall and make the connection that way so that you don't necessarily need line of sight. And then do handoffs. And you know, essentially once you've done that, you've got an access channel. And also get rid of that lens antenna, shrink the form factor, you know, get the chip-scale antennas working. So it's an exciting path that I think we're on to show that it'll work. And then, you know, will the use cases come? Well, we'll see. We'll see. So, thank you. Any questions? Yes.
Yeah, I have 2 questions.
Yeah.
Let me ask one after another. First one is the mobility issues for millimeter wave wireless in the presence of non-line of sight. The demo that you showed actually is a controlled experiment.
Yes.
The second question actually is, I read somewhere that operators are strongly not in favor of using a fiber quality links to basically connect the remote radio heads with the centralized RAN, mainly because in democratic nations it's simply not possible to deploy whatever these. So now going forward to 5G, what kind of challenges that you see in getting the front haul, and then do you see significant increase in the front haul rate requirements? Yeah.
So if I could kind of repeat the 2 questions. So one of them had to do with this in the centralized RAN, this problem of connecting fiber to your antennas, right? The second one was right. So let me answer the first one, or the second one first, and the first one second. And so in the millimeter wave, so here's the thing. This is very important about 5G, I think. Again, you're going to have a number of narrow use cases. And each one of those use cases will probably have a technology that's tailored to them. And 5G will integrate them all. Okay? Because we're no longer in the world where you put up one kind of technology on the top of a tower and everybody's happy. I just don't think we're in that world anymore. So The narrow use case that we're talking about with millimeter wave is, again, this sort of ultra-dense, and again, we're not using data this way today. Okay, there's no need for this today, so I understand why it's difficult, but imagine a world where, you know, a significant portion of the population does want high data rates a lot of the time, and we're in this conference room here, and you know, there's not enough coverage, right? And maybe Wi-Fi can't cover it. So it's possible that'll never happen. It's possible it won't happen until 2050. I don't know, but that is the intended use case. For the centralized RAN, again, it is a somewhat narrow use case, but in stadiums today, stadiums use DAS systems today, as you know. You probably know. Those antennas in that DAS system are connected over fiber. So they have to actually run 2 fibers out so to get the main and diversity branch for LTE. So they're paying for that today. So all the major stadiums have DAS systems, and the centralized RAN works perfect with the DAS systems. I mean, that's your remote antenna right there. Now, in a building like this, let's say you had a large conference room and you wanted people to be able to have very high data rates and so on. Again, I think it's economically feasible to run fiber within the building to remote antennas. I think that's the use case. Now, running fiber outside, yeah, that's expensive, I agree.